What are the chances of the inner planets of our solar system colliding with each other? The basis for this question is the chaotic nature of their orbits that raises the possibility of the occurrence of such a catastrophic event. To know how stable our solar system is and why it is so, I am at the Paris Observatory to speak to Federico Mogavero, who recently co-authored a research paper on this subject.
Since 1989, we know that the motion of the planets in the solar system is chaotic. Chaos means that we cannot predict the future positions of the planets in a precise, deterministic way beyond basically the next 60 millions of years. The origin of this chaotic behavior of the orbits lies in the existence of some resonant gravitational interaction. The unpredictability due to chaos affects the small inner planets a lot. We are talking of Mercury, Venus, the Earth, and Mars. Over the next hundreds of millions of years, their orbit will practically change in a random way. In principle, this random variation could be dramatic, leading, for example, to a planetary collision. This situation can be imagined as we had a flock of ships, blindfold ships, wandering close to the edge of a steep cliff. We expect that one of them would readily plunge off the cliff. In reality, computer simulations show that the probability of a catastrophic event, such as a planetary collision, is unexpectedly low. Just one chance in 100 over the next 5 billions of years. This is a very long time scale, which is comparable to the age of the solar system and to the remaining lifetime of the Sun. To have a 50-50 chance of a catastrophic event, you should wait more than 30 billions of years. That is longer than the age of the universe, and that's astonishing. It's as if our ships wandering along the cliff took a random step each minute and were still perfectly safe after an entire day. In our latest research, together with my collaborators Nam Wang and Jacques Lascar, we tried to explain the reasons for this great stability of the inner solar system over the next billions of years. We find out that even if the planet motion is chaotic, there is still some order out of this chaos. We unveil the existence of some hidden symmetries in the way the planets interact with each other, and these symmetries make the dangerous changes in the planetary orbits happen only on very, very long time scales. To arrive to this explanation, a couple of years ago, we developed a simplified model, but still a very realistic one, of how the orbits of the planet will evolve on very, very long time scales. The essential idea here is to forget about the precise position of the planets around the Sun and to focus on how their elliptical orbits, predicted centuries ago by Newton, will change their orientation in space and their shape over time. And this kind of long-term orbital evolution can be simulated very fast with a computer, and our latest research lies on thousands of these numerical simulations covering up to 100 billions of years. And the entire set of this simulation took almost 1 million hours of computing time.